Hello, everyone. Allow me to introduce myself. I am Charles Antony Raj. I'm a senior manager for systems and software engineering at Collins Aerospace, an RTX company. Today, I'll be talking about a critical frontier in sustainability, the role of electrical systems in aviation, and how data and innovation are shaping up lower emissions for the future for the skies. Let's start with the problem we are trying to solve, the climate challenge, aka the emissions challenge. The aviation industry is increasingly recognized as a significant contributor to climate change, both in terms of CO2 emissions and other non-CO2 effects such as contrails and nitrogen oxides. While aviation may currently account for a smaller share of global greenhouse gas emissions compared to other sectors, approximately 2.4% of global anthropogenic CO2 emissions, its environmental impact is far from negligible and it's growing rapidly. To put this into perspective, commercial aviation emitted about 918 million tons of CO2 in 2019, marking a humongous 29% increase in emissions since 2013. Even more concerning is the projected trajectory of aviation emissions. Without aggressive interventions, including advances in aircraft efficiency, sustainable aviation fuels, operational improvements, and policy measures, aviation emissions are expected to increase by 300 to 700% by the year 2050. Electrification isn't just theoretical. It's already making an impact in early application and pilot programs. Fully electric short-haul aircrafts for regional flights under 500 kilometers, emerging all-electric aircrafts like the Aviation, Alice, and Hart Aerospace ES-30 offer emissions intensity reduction of up to 80%. While conventional regional jets emit roughly 150 to 180 grams of CO2 per passenger kilometer, fully electric aircraft can bring this down to 30 to 50 grams. Hybrid electric aircraft, combining electric motors with conventional engines or generators, are seen as a bridge technology for the 2020s and 2030s. These systems can already reduce fuel burn by 8 to 12% on short-haul routes. Hybrid configuration allow for battery-assisted takeoff and climb, the most energy-intensive phases of flight, reducing the load on fuel-burning engines and lowering emissions. When we talk about electrification in aviation, we are no longer operating in the realm of theoretical future tech. What was once a domain of R&D labs and speculative prototypes is now making the leap into real-world implementation and market adoption, and it's happening faster than many predicted. Market adoption is accelerating by 2030. Projections indicate that 200 to 300 electric aircraft could be in active commercial or regional service around the world. These are not drones or experimental vehicles, but actual passenger-ready aircraft certified and operating short-haul routes. By 2050, electric and hybrid electric aircraft could account for up to 24% of all aviation activity, particularly in the short to medium haul segments. Investment is flowing into the sector big time, the clearest sign that the industry is serious. Capital is following innovation in a big way. In 2022 alone, over $8.7 billion was invested globally in sustainable aerospace technologies. Of this, roughly $5.3 billion, more than 60%, was directed towards electric and hybrid electric startups. Let's look at one of the real-world successes, the Pipistrel Velis Electro, first fully electric aircraft in the world to receive EASA type certification. This aircraft is in service in over 30 countries used by flight schools, research institutes, and other operators, clocking in more than 5,000 hours of flight hours, which is 40 tons of CO2 saved. Ground operation impact. Let's talk about that. Taxiing is a deceptively high impact phase of flight. Typical commercial aircraft spend 10 to 30 minutes taxiing between gate and runway per flight. During this time, main jet engines are often idling, consuming up to 5 to 10% of total fuel used on short-haul routes. The solution could be an electric taxiing system. It's an electric taxiing system decouple ground movement from the use of main engines by using electrical motors installed in the landing gear or driven by electrical tow vehicles. The key benefits are, you could have up to 4% fuel savings per flight, lower carbon emissions, of course, reduced noise pollution at the airports, improved engine life cycle and maintenance, operational flexibility. The critical challenges ahead. Battery energy density, the physics bottleneck. Today's lithium-ion battery packs achieve only 200 to 250 watt-hour per kilogram at the system level. As a result, fully electric aircraft are currently viable only for short-haul routes. Scaling electric propulsion to medium and long-haul flights will require next-generation energy storage solutions. Electrification doesn't stop with the aircraft. It fundamentally reshapes airport infrastructure. A typical regional airport supporting electric operation would require 30 to 60 megawatts of charging capacity to support multiple aircraft charging simultaneously. To put this into context, that's roughly the peak electricity demand of a small city. This demand raises multiple challenges, like grid upgrades, charging logistics, and energy sourcing, to name a few. Last, but by no means the least of the challenges, certification and regulatory challenges. Regulatory frameworks are still evolving. Agencies like the FAA and ESA are working to define new rules for electric and hybrid electric propulsion systems. Let me finish by saying this. The road to zero emission aviation is complex and multifaceted, but electrification represents a key pillar of this transition. The next 2 decades will be critical. With continued investment, regulatory support, and technological breakthroughs, electric aviation can play a meaningful role in decarbonizing the sector and delivering a cleaner, quieter, and more efficient future for air travel. Thank you.